Electronegativity is often discussed in high school and undergraduate classes. In general, you learn it's a property of atoms, it affects bond polarity, how it roughly trends in the periodic table, and that's about it. Here we'll talk about where electronegativity values come from and how those values were calculated. More importantly, we'll talk about what it really means. You may not realize you can use electronegativity to calculate important properties of molecules like bond energy. There's even a charge scheme based on electronegativity so that you can calculate consistent charges in molecules. In other words, if Hamlet was looking at what most people are taught about electronegativity, you might say, there are more things in heaven and earth than you're dreamt of in your undergraduate textbook. Electronegativity isn't something that falls out of the math from quantum mechanics. It isn't a property that we have one set way of measuring, so there are different scales that have been devised. Here, we'll briefly discuss 3 different flavors of electronegativity. Pauling electronegativity, the original and probably still most talked about, Sanderson Electronegativity, in my opinion the most useful, and Allred-Rochow Electronegativity, which gives a good description of what electronegativity means. A good definition of electronegativity is the ability of an atom to attract electron density in a bond. To illustrate, you can look at what we call the bonding molecular orbital for a simple system. This is where the pair of electrons bonding the 2 atoms together is residing around the 2 nuclei. This is what it looks like for H2. The 2 white balls indicate the positions of the hydrogen nuclei, and there's an evenly dispersed electron cloud around them shown with the blue mesh. The 2 atoms have the same electronegativity, so they attract electrons the same way. Fluorine has a higher electronegativity than hydrogen, so let's look at HF and its bonding orbital. Here the light green ball is the fluorine nucleus and the white is hydrogen. The cloud is obviously distorted towards the more electronegative fluorine atom. You might think that maybe the electrons are distorted towards fluorine because it just has more electrons than hydrogen, but this is just the 2 electrons in the orbital bonding the 2 nuclei together. Even so, we can look at IF, where fluorine is bound to iodine. This time iodine has far more electrons than fluorine, but fluorine is far more electronegative, and the bonding orbital still distorts towards the light green fluorine and away from the purple iodine. Pauling won the Nobel Prize in Chemistry in 1954 for his research into the nature of the chemical bond and its application to the elucidation of the structure of complex substances. He has the distinction of being the only person to ever win 2 individual Nobel Prizes, this in chemistry and the Nobel Peace Prize in 1962. Pauling electronegativity is derived ultimately from bond energies. The insight can be explained by trying to understand the energy of a heterodiatomic like HCl as the arithmetic mean of the pure covalent homodiatomic H2 and Cl2. If we say there is some inherent bond energy that the atom has when covalently bonded, that energy is retained when we go from a nonpolar bond to a polar bond. In other words, the inherent covalent bond energy of hydrogen is half the H2 bond energy, and the inherent covalent bond energy of chlorine is half of Cl2's bond energy. So when we make HCl, would the bond energy just be the sum of these inherent covalent bond energies for hydrogen and chlorine? Not quite. What Pauling discovered was that the real bond energy is always higher than that expected for the covalent bond energies. As a result, he postulated that there must be some ionic effect that adds to the covalent bond energy. In other words, polarizing the bonding electrons, like we showed earlier, leads to an additional stabilization. His equation from his famous book, The Nature of the Chemical Bond, looks like this, where Be is the bond energy and Chi-Ap is the Pauling electronegativity of atom A. The constant 23 converts from electron volts to kcals per mole. The second ionic part of the equation increases as the difference in electronegativity increases. In other words, the bond energy increases as the polarity of the bond increases. If we apply this to a diatomic like HCl, we can see how Pauling electronegativity can be used to calculate bond energies. The bond energy for hydrogen, BeHH, is 104.2 kcals per mole, and the bond energy for Cl2 is 58 kcals per mole. The Pauling electronegativity of chlorine is 3.16 and hydrogen is 2.20, so we can plug in those values. The covalent bond energy in HCl is 81.1 kcals per mole. Added onto this is some additional bond energy due to the polarity, about 21 kcals per mole. The full bond energy is the sum of those two, or 102.4 kcals per mole, which can be compared with the experimental bond energy for HCl, which is 103 kcals per mole. This is really good agreement, but Pauling electronegativities come from bond energies, so to some extent, they're repackaging the bond energies. However, the repackaging contains some incredibly insightful ideas about how bonding works. Calculating Pauling electronegativities can be done using the equation above if we have enough experimental bond energies and assign some electronegativity to some atom. Pauling assigned an electronegativity of 4.000 to fluorine. In other words, if we want to find a Pauling electronegativity of hydrogen, I need the bond energy of H2, F2, and HF. I put those in the equation, and after assigning the Pauling electronegativity of fluorine to be 4, I have an equation with only one unknown, the electronegativity of hydrogen. From here, you can start to build up electronegativities for the whole periodic table. R.T. Sanderson derived a completely different scale for electronegativity. While Pauling's values came from bond energies, Sanderson's numbers are based on the electron density of the atom and an ideal electron density for each atom. The ratio of the two gives you an idea of if the atom wants to add or subtract electron density, which he originally called the stability ratio. A simple equation can be used to calculate the electron density of the atom in electron charges per cubic angstroms. The electron density of atom A, zeta A, is just the number of electrons in the neutral atom, which is the atomic number Z divided by the volume of the spherical atom. The covalent radius was used for the radius of the sphere. So we can easily calculate the electron density of the atoms, but what is the best electron density for some element to have? For this, Sanderson made an interesting assumption. He assumed that the noble gases are not less reactive just because they have filled shells. He suggested they are also at their ideal electron density. To find the electron density of the rest of the atoms in the periodic table, he just said that the elements in between could be found by interpolation. In order to find the inert electron density of lithium, we need the equation of the line defining the noble gases on either side of lithium, helium and neon. We draw a graph with the 2 points using the atomic number Z and the electron density. For helium, this is Z equals 2 electrons and the electron density equals 0.59 electrons per cubic angstrom. For neon, Z equals 10 electrons and electron density equals 1.06 electrons per cubic angstrom. For these 2 points, the line looks like this. We use this line to find the ideal electron density of lithium by inserting Z equals 3 into the equation. This gives an ideal electron density for lithium of 0.65 electrons per cubic angstrom. Sanderson electronegativity, or Chi-S, which was originally the stability ratio, was just the electron density of the atom over the ideal electron density. Let's calculate the electronegativity of fluorine, just to show how this might be done. Plugging in Z equals 9 and a covalent radius of R equals 0.72 angstroms, we get that fluorine has an electron density of 5.75 electrons per cubic angstrom. Fluorine has an atomic number of 9, so we can use the same equation between helium and neon that we used before. This weirdly, and what I assume coincidentally, gives an ideal electron density for fluorine of 1.00 electrons per cubic angstrom. The Sanderson electronegativity is the ratio between these two numbers. I can even do this one in my head. 5.75 divided by 1 is 5.75. Because Pauling's scale was so popular, Sanderson later scaled his electronegativity value so that fluorine was equal to exactly 4. The relationship between Pauling and Sanderson electronegativity is slightly nonlinear. Sanderson developed a method to calculate bond energies and other properties to fairly high accuracy using these electronegativities, which is just called theory of polar covalence. The process is a little more involved than the Pauling calculation above, but there's a lot of nuanced information about bond energies built into the method. As a result, it won't be discussed here, but is well worth its own video later. The final scale we will discuss was developed by A. Louis Allred and Eugene G. Rochow. They based their scale on Coulomb's law. Charles de Coulomb was a French officer and physicist who lived from 1736 to 1806. Coulomb's law describes the relationship for force between two particles with electric charge and distance. There's an inverse square relationship between the distance and the force. The distance that Allred and Rochow used was the covalent radius of the atom, R. The idea that they had is this. Since electronegativity is the ability of an atom to attract electrons in a bond, the best measure of electronegativity would be to look at the attractive force between the atom and another electron, like the one that might be donated by another atom coming in. This attraction that the atom has for another electron is electronegativity. Basically, the reason HF has a bonding orbital that looks like this is because fluorine is attracting more electrons to itself than just the 9 it comes in with. So let's just get a measure of the attractive force for that 10th electron. The number of protons in the nucleus is generally given the capital letter Z. So fluorine has 9 protons, or Z equals 9. However, there are 9 electrons around the nucleus in the neutral atom, so do they cancel all the charge of the nucleus? Oddly, no. If we have a neutral spherical fluorine atom, it might look something like this. The idea is we bring in another 10th electron at the covalent radius. From the viewpoint of the incoming electron, there are 9 positive charges in the nucleus, z equals 9, and there are 9 electrons surrounding the nucleus. However, those electrons aren't all between the nucleus and the incoming 10th electron. Some are spending time on the other side of the nucleus where they don't cancel out a full positive charge from the nucleus. As a result, there's a residual positive charge from the nucleus that the electron is attracted to. We say the electrons don't perfectly shield the nucleus. As a result, there's an effective nuclear charge that remains that isn't canceled by the electrons, which we just call Z effective. One can estimate the shielding and calculate Z effective using what are called Slater's rules. In essence, the electrons in different orbits around the nucleus cancel different amounts of the proton charge in the nucleus. There's a way of roughly calculating this, which we won't go into in detail here, but the point is that there's always some residual positive charge on every atom. Then they took Pauling electronegativities and fit those to Z effective over R squared with the equation here, where m is the slope and b is the intercept. You get a very strong linear correlation with a slope equal to 0.359 and the intercept of 0.744. As a result, we have an approximately experimental method for finding electronegativity just based on covalent radii and Coulomb's law. I say approximately experimental because we rely on Slater's rules to give us the Z effective values, which were derived semi-empirically and aren't expected to be absolutely precise. Sanderson even said that Allred-Rochow scale would be the ideal electronegativity scale, if the shielding values could be precisely found. There you have 3 different flavors of electronegativity. The scales are quite useful conceptually and are a significant part of how we understand two-center two-electron bonds. In future videos on this topic, we could discuss how to use Sanderson electronegativity to calculate charges in a molecule and how to get quite accurate back-of-the-envelope bond energies. Thanks for watching. If you enjoyed this video and want to support future videos covering topics like this one, please subscribe to our channel and give us a thumbs up. We make these videos for fun and as a way of interacting with and giving back to the community, so we greatly appreciate your support.